All right, welcome back to CS50. This is week 3, and on the evaluations at the end of last fall, we got a comment from a student about how they apparently were incentivized to come to class early simply because we started most every lecture with a little something stupid. So I thought we'd begin 2 minutes early so that we can squeeze in 2 such minutes of motivation. This one related, of course, to problem set 2, which for those of you doing the Hacker Edition, challenges you not to implement ciphers, but to do the reverse, cryptanalysis, and actually decrypt some known people's passwords. So with that, I give you this perhaps famous clip.
What's going on? What are you doing to my daughter?
Permit me to introduce the brilliant young plastic surgeon, Dr. Philip Schlotkin, the greatest nose job man in the entire universe and Beverly Hills.
Your Highness.
Nose job? I don't understand. She's already had a nose job. It was a Sweet 16 present.
No, it's not what you think. It's much, much worse. If you do not give me the combination to the air shield, Dr. Schlotkin will give your daughter back her old nose.
No! Where did you get that?
All right, I'll tell.
No, Daddy, no, you mustn't.
You're right, my dear. I'll miss your new nose, but I will not tell him the combination no matter what.
Very well. Dr. Schlotkin, do your worst.
My pleasure.
No! Wait! I'll tell.
I knew it would work. All right, give it to me.
The combination is 1,
1,
2,
2,
3,
3,
4,
4,
5.
5. So the combination is 1, 2, 3, 4, 5. That's the stupidest combination I ever heard in my life. That's the kind of thing an idiot would have on his luggage.
Thank you, Your Highness.
What did you do?
I turned off the wall.
No, you didn't. You turned off the whole movie.
I must have pressed the wrong button.
Well, put it back on. Put the
Yes,
movie
sir.
back
Yes,
on.
sir.
You gotta get that thing fixed. We're back, and we have the combination. Schlotkin.
What?
We're done with you. Go back to the golf course and work on your putts.
Let's go, Arnold. Come, Gretchen. Of course, you know I'll still have to bill you for this.
Bet she gives great helmet.
Well, did it work? Where's the key?
It works, sir. We have the combination.
Great. Now we can take every last breath of fresh air from planet Druidia. What's the combination?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yes.
That's amazing. I've got the same combination on my luggage. Prepare Spaceball 1 for immediate departure.
Yes, sir.
And change the combination on my luggage.
OK, it really doesn't get stupider than that. So this is CS50. We left off last week looking at cryptography, the motivation for which ultimately was to introduce a problem domain for problem set 2. But more than that, it was to make clear this reality that if you've already sat down to tackle P set 2, or will soon this week, what's ultimately a fairly interesting idea, taking plain text, converting it to ciphertext, and generally doing something useful, encrypting information, it really reduces to some things that are very, very simple. You're going to find that taking in plain text is a matter of calling something like getString, which of course returns to a string, which of course is just an array of characters. Well, encrypting text then is really going to reduce itself to just iterating over that array from I equals 0 on up to the length of the string, and then doing some kind of manipulation of each of the characters. Maybe in the case of Caesar, some addition. But there's a problem with the Caesar cipher. So the Caesar cipher is this algorithm via which you take some text and quote-unquote rotate each of the characters by some number of places. And ROT13 was a very specific instance of that, where the secret rotational value, the so-called key, was in that case 13. But we can generalize. It can be anything from 0 on up to infinity. But of course, only a few of those, say 26, actually have some utility. How would you go about cracking, that is, figuring out someone's password if it were encrypted with the Caesar cipher? If I hand you a string of text, it looks like nonsense because it's been encrypted with ROT13. not twice, but once, what would you do? What's that? OK, so frequency analysis. So a fancy way of saying, well, there's some letters in the alphabet that are more popular than others. If you've ever watched Wheel of Fortune, you'll realize that most contestants know this. So maybe you look for the most frequently recurring letter in the ciphertext and realize, Q. Q appears an awful lot. But wait a minute, this has been encrypted. It's probably the case that Q is the result of encrypting a more common letter, maybe E, for instance, and getting Q as a result. So you might be able to reverse engineer what the secret key is by making some inferences. Or even if you're not that clever, and you've never heard this term frequency analysis, but you know it's been encrypted at least with Caesar, I mean, what is another approach, a correct approach, if naive approach even? Yeah. Yeah, there's only 26 keys that might have been used if we're talking about Caesar. So yeah, it might be a little tedious, but it's not going to take forever just to try all possible keys. And in fact, you don't have to try all possible keys on the entire message, especially if this is a whole letter or paragraph or whatever that's been encrypted. Try the first few letters. And if you start seeing English pop out, or maybe French or Spanish or anything that can be expressed with A through Z, odds are if it looks like a word, if it looks like a sentence, bam, you found the key. So Caesar is not all that strong. And maybe it was, in fact, used back in the day, but there have been certainly improvements on it since, because even we with a piece of paper and a pencil could crack the Caesar cipher. Well, the Visionaire cipher, which came along some years later, is a little more sophisticated. It takes the approach of Caesar of rotating letters in the alphabet by some number of places, but of rotating different letters by a different number of places. So instead of using K, the key, the numeric key, to encrypt every single letter in your plain text, it uses a different key for each successive letter. Now, that doesn't go on forever. You usually pick a fixed number of keys. And in fact, if you just need a fixed number of keys, you just choose what we'll call a keyword. So something like foo bar. Now, as an aside, if you've wondered why I constantly resort to foo and bar and baz and all of these strange names for variables, you'll find that this is just a silly computer science thing, a silly programming thing, a convention. Whenever you need to whip out a random variable for the sake of discussion, foo is typically one's first instinct. Bar followed by that, and then baz, and then quux, and then there's a whole bunch of silly ones after that. So foo bar is sort of a canonical example of a random word that we might use, but we just have to realize that each letter in foo bar, in this case, just represents a different key. So F represents one key, O represents another, O happens to represent the same, B is another key. So in other words, you take your keyword, you line it up under your plain text, and you rotate each of the plain text characters by the number of places implied by the key. So now what is F? Well, let's see. If we start counting at 0, as we typically do, A is 0, so that's B, C, D, E, F. So F represents the number, the key 5. So what does that mean? Well, if my plain text P is hello world, and I need to rotate H by F, that is by 5 places, I go H, I, J, K, L, M. OK, so the resulting ciphertext letter is M, and then I repeat that same process using different keys. Now, presumably, my plain text, the message I want to encrypt, is hopefully going to be longer than the key. If you're remembering a key that's longer than your actual message, you're losing some efficiency there, perhaps. So foo bar is only 6 letters. So what if our plain text is longer than 6 letters? Well, you just start repeating again and again and again. So let's ask the question for just a moment then. If there are 26 possible keys for Caesar, how many possible keys are there for Visionaire by contrast? A little louder, a little more confident. OK, infinitely many. So certainly, because we can pick any possible keyword of any length. But let's generalize. Suppose that we have n letters in our keyword for Visionaire. How many n-letter keywords are possible for Visionaire? Right, so 26 to the n. So if you have an n-letter keyword, 6 in this case, and each of those letters can be A through Z, to any of 26 possible letters, you've got 26 options times 26 options times 26. So that's 26 to the n. And then if I relax the constraint that the key is 6 letters, and I say, the key is any number of letters, then you have even more. You have 26 to the 2 plus 26 to the 3 plus 26 to the 4. So in short, the key space is a lot larger. Now, ultimately, you could still crack the Visionaire cipher by a few ways. You could do some intelligent manipulation. You could look for patterns, for instance. You could do frequency analysis, some fairly sophisticated heuristics, or you could try all possible keys. Start with all the one-letter keys. Then once you've tried all those and gotten back nonsense, try all the two-letter keys, the three-letter keys. And that algorithm, though naive, would eventually work, at least in theory, if you have enough time to wait around. Now, unfortunately, these days, when you've got 2 gigahertz of power underneath your own desk or in your laptop, you can churn through a lot of keys very quickly. And in fact, there's this algorithm called DES. DES. And this is actually an algorithm that's used in the function that's typically used on a Linux or Unix or Mac OS system still today to encrypt your own password. So you've got a username and password maybe on your own computer, certainly on nice.fas.harvard.edu now. And your password, fortunately, is stored in encrypted fashion. And this is why, for instance, the user assistants, beg them as you might, cannot tell you what your password is if you forget it, because the system stores it in encrypted fashion. So this algorithm, this function called DES, was used for some time, many years after Visionaire, but in more recent modern times. And there were, with DES, 72 quadrillion possible keys because of the number of bits used to encrypt something with this particular algorithm. Now, we won't go into the specifics. I put this little snippet from a textbook just to kind of hint at the relative complexity of this. Visionaire is very simple. You can do it paper pencil. DES starts to take a computer or a calculator, as all of these arrows in this flowchart generally implies. But a computer can compute DES encrypted text fairly quickly. Unfortunately, too quickly. So the reality is these days, if you encrypt something with DES, if someone has enough free time and enough CPU cycles at their disposal, they can crack your password. And that's, in fact, exactly what Problem Set 2's Hacker Edition is all about. Now, this is, interesting, maybe fun in the context of passwords on some random university's system. It's a lot more worrisome if random people, if students in CS50 with a laptop on their lap can crack information that has been encrypted with something like DES. DES is not very secure anymore. 56-bit keys, as it once used, no longer very secure. So there are variants. In fact, someone came up with the bright idea of not just using DES, but let's run DES 3 times. Call it triple DES or 3DES, and that actually is a little more secure, but not terribly so. So the world has come up with more sophisticated algorithms. And if you take or have time to take over your years here, Computer Science 120, which is a cryptography class, and there's some graduate level ones. It's a really interesting space. But the funny thing is, a lot of the security of today's cryptographic mechanisms ultimately boil down to assumptions. The safety of them boils down to assumptions. In other words, there is this algorithm called RSA. And you might have seen this listed on various websites. You might have heard of this algorithm before. It ultimately boils down to a really fancy way of allowing websites to communicate with browsers securely. But that's just a specific case. You can use it for far many more interesting purposes. ATM machines, bank transactions, a whole bunch of interesting stuff. But it ultimately, the security of RSA, whether you're using keys that are 56 bits long, which is pretty short these days, or 128 bits long, or 1,024 bits long, ultimately, whether or not this algorithm actually works reduces to whether mankind can come up with a fast way of factoring large numbers. So again, long story short, this algorithm called RSA boils down to assuming that mankind and their computers cannot take a really big number and factor it really quickly into 2 large prime numbers. So put another way, if you want to encrypt some information and you want to use an algorithm like RSA, you take 2 really big prime numbers. And it's not hard to generate prime numbers, even big ones. It's not hard to multiply them together. But it is much harder to undo that process when all you do is hand an adversary or hand a computer a really big number and then say, hey, this just so happens to be the product of 2 really big primes. Tell me what they are. We, thus far, have not come up with a relatively fast way of figuring that out. It will take more minutes than we have in our lifetimes, for instance, to make sweeping generalizations. But the key is, no pun intended, that there's a lot of interesting opportunities to improve upon or even break some algorithms that the world itself is now entrusting our money, our security, and a whole bunch of things to. To give you a sense of what a bigger key looks like, so this is intentionally rather small and deliberate. This is a key, a really big number that happens to be represented with alphabetical characters and numbers, just for efficiency's sake, that represents a key one might use with an algorithm like RSA. This is a lot bigger than a number from 1 to 26. This is a lot bigger than a keyword like foobar. So this hints at the types of security that's actually in use today. And so that's where we pick up today. So we've spent a lot of time the past couple of weeks talking about syntax and C and programming. But now finally that we've gotten some of the minutiae out of the way, what a for loop is, what a while loop is, and granted you might still need another week or two of practice to get comfortable with even those syntactical details, we finally now have the ability to start talking at a slightly higher level about how you actually start to think more effectively, as the syllabus and course catalog claims, how you can solve problems more efficiently, as is the other promise made. And we started this course with this sort of visually interesting example of taking a really big phone book, and I claimed that I could find Mike Smith much faster than, say, a completely naive person would by starting at the front and flipping through the A's, and then the B's, and then the C's, because I took this approach of dividing the problem in half and conquering only half of it. And then I realized, oh, if Mike I know is in the right-hand side of the phone book, let me do this again and split the problem again and again. And our takeaway was that if that phone book, and it pretty much was 1,000 pages or 1,024 pages, how many times would I actually have to split that problem in half to find someone like Mike Smith? So just 10. Right? If you have 1,024 pages and you just do the math in your head or on a piece of paper, you can divide that number in half 10 times. Now, there might be some interesting rounding issues at the end when you get to the last page, but 10 times instead of 1,024 pages. Suppose that phone book, as we said in week 0, were not 1,000 pages, but 4 billion pages. That's a hell of a phone book with a lot of names in it. But how many pages would I actually have to look at? How many times would I have to chop a 4 billion page phone book in half? So 32 times. Why? Well, you can take 4 billion and divide it in half roughly 32 times. And that speaks to the power of actually designing algorithms intelligently. That speaks to the power of what you can do with these basic devices with just a modicum of intelligence inserted into your algorithm. Right? If I told you to search a phone book right now, you could certainly reason through how you might implement divide and conquer. But by far, the simplest way to implement search for a phone book using the syntax and the capabilities of C you have now is what? Like write a for loop, I gets 0, I less than or equal to 4 billion, and then just check from I on up to 4 billion whether or not someone is in the current variable or in the current array or however you actually code it up. You could implement that with just a few minutes time, but that thing's going to take a while to run. By contrast, put a little more thought up front and the algorithm itself will execute far more quickly. So we're not going to stand up and indulge in this again, but this was an instance of this same idea. The first day, you all stood up, you paired off with someone, and then half of you sat down. Then half of you sat down. Then half of you sat down. Now, granted, that turned into a bit of a disaster, as is often the case. Took way longer, I think, than for me to just go 2, 4, 6, 8, 10, 12. But in theory, had there not been the social awkwardness, had there not been the problems with arithmetic, you would have been able to count the people in this room so much more quickly than I, because whereas I'm sort of going like this, 1, 2, 3. So with every CPU cycle, I'm doing one thing. You, by contrast, with every toll of the clock, with every CPU cycle, half of you were sitting down. You were taking 50% of the problem out of the room at once, where I was just taking 1/10 of it out of the way. So this, too, has implications. So this is just a fancy way. I whipped this up with Excel to depict the following idea. So on the x-axis here is this number n, which generally is going to refer to the size of the problem. How many pages are in the phone book? Let's call it n. How many students are in Sanders? Let's call it n. So I have from 0 on up to 130. And then on the y-axis, I have what I call t of n, the running time of an algorithm whose input is of size n. So it's just a general way of describing the running time. How much time does it take for an algorithm to run? And what do we mean by time? Like steps or seconds, minutes, whatever, so long as we all agree what the metric is. And these different lines represent different running times. So at the top left, we have a little legend there. It's kind of small to see, but we have 3 graphs here. One is this one up top. So on the left-hand side, we have a very steep curve, but this is a line. This is a linear graph, and this represents a algorithm that, given n inputs, takes n steps to run. And that is representative of the running time of 1, 2, 3, this linear algorithm of counting students. But we realized in week 0 we can do better, right? We can actually speed things up. So the second graph there, the second line that's a little bit to the right of the first one, that would be the result of my doing 2, 4, 6, 8. It's actually twice as fast. But now contrast this with your line. So log of n, as we described your algorithm that day, as we described this general principle of divide and conquer, what this means is that your algorithm should take way less time. In other words, the more students are in the room, look at the contrast between how many steps or how many seconds, how many units of time your algorithm should take versus mine, which is literally off the charts. Now, what does this mean? If one more student comes into this room, that takes me one more step. If one more student comes into this room, that's kind of rounding error for you, because you can kind of subsume that one additional student. So let's actually let's increase the problem more significantly. Suppose we have roughly 300 students in this room. Suppose another 200 or 300 students come into this room within the next few seconds. Well, that's going to take me literally twice as long. If it took me n steps before, it's going to take me 2n steps by doubling the size of the room. Now, by contrast, if 200 or 300 more students enter this room in the next few seconds, how many more steps or unit of time does it take you to count those additional students? Just one, right? Because within the first iteration of your algorithm, those same kids will sit down right away. And that's a huge bite out of the problem, whereas mine has grown significantly. And that's the fundamental contrast between something that's linear, like in my case, and something that's logarithmic, or at least mathematically more interesting. And not to overwhelm with numbers, but just to put concrete values at what the implications here are. This is just a big chart that computes some very basic functions. So in the left-hand, the third column here, right above where I'm standing, this is n. So we arbitrarily have 1, 2, 4, 8, 16, a whole bunch of values of n. So my algorithm, 1, 2, 3, 4. If we have, let's say, 1 million students in this room, or 1,048,576, that's obviously going to take me 1,048,576 steps. But by contrast, if you scroll back to the left, and you can do this with a calculator or even in your head perhaps, that same student body of 1 million students in Sanders could be counted by you all in just 20 steps. And so the takeaway visually of a graph like this, and we'll revisit this, or you can revisit this as we introduce yet more algorithms, is exactly how significant the implications are of well-designed algorithms. And we can zoom out even further. If you look at various graphs like these three here, the specifics are not so interesting today, but notice this last one here. So it's small to see, but that big curve that's going to the north there is called 2 to the n. 2 to the n being an exponential function. So we'll talk about at times, and in future classes, if you take other theory classes in CS, even if just for fun or for minoring in CS, you'll find that exponential algorithms very bad, because as n increases, they take a ridiculous amount of time. But back to our motivation today of cryptography, when we say it's really hard to factor large numbers quickly, what we mean essentially is that factoring large numbers generally boils down to doing something that takes exponential time, not linear, not quadratic, not polynomial, if you recall the terms, but exponential. So graphs like that, very bad. Takes a good amount of time to run. So how can we start to describe the running times of algorithms, right? It's easy enough to pick a few examples, talk about which one's better, why it's better, and how many steps it takes. But can we generalize? Can you start to look at your own code or your own programs and say, this algorithm is good because it takes this amount of time, or this implementation I wrote last week sucks because it takes this much time in general? Can we slap some labels or some formalities on just so that we can start comparing algorithms against one another, even if written in different languages or written by different people? Well, there's three basic constructs, three little pieces of jargon we'll start using. One is called big O, and that's the guy at the top. The middle guy is called theta, and the bottom is omega. And these symbols are just generally used by mathematicians and computer science to express the running time of algorithms. Now, what does this mean? So formally, it means this. And these slides are online if you like the mathematical formalities, because there's actually some juicy ideas in there. But for today, they've reduced to some relatively simple ideas. If you have an algorithm that in the worst case takes n steps, you say that that algorithm is in big O of n. So this is the worst case running time of my linear algorithm of counting students. And as an aside, happy birthday to Jansu and Mike. If, though, your algorithm in the best case might actually take fewer steps, well, then you start talking about omega notation. Now, in the case of counting students, this really doesn't help us. Because in the best case, how many steps is it going to take me to count n students? Well, n, right? I kind of have to count everyone. And in the best case, well, if I want to count all of the students, it's still going to take n steps. But let's pick another algorithm arbitrarily. Suppose as students file into the room, I want to search for a student named Mike, just because. So in the worst case, how many steps will it take me to find a student named Mike as they file in the door? All right, so n steps, because in the worst case, the Mike or the several Mikes we have in the course this semester are just so happen going to be the last people coming into the room, just by chance. But in the best case, where might Mike be in the line? So first, right, just common sense. So in the best case there, we say that that algorithm of finding Mike, searching for Mike, is in omega of 1. In the best case, it just takes one step because, bam, I ask the question, I get the answer I'm looking for right away. So when you have an algorithm that is both in big O of n or in omega of n, so not the searching, but rather the counting, then can you say that that algorithm is described by theta of n? So in short, we have worst case running time up top. We have best case running time at bottom. And if those two just so happen to be the same, then you can say that the algorithm is in theta of whatever formula you've come up with, n in that case. All right, so what does this mean exactly? So in the case of a phone book, when I toured the phone book again and again and again, what was the running time of finding Mike Smith, or really finding anyone for that matter, in a phone book that happens to have n pages? In the worst case, searching a phone book takes how many steps? OK, so log n, if my algorithm is to just start at the first page and go from left to right all the way to the end of the phone book. So that might be one implementation. And this will be, say, linear search of a phone book. But we can do better. In other words, if I want to compare one algorithm, the linear algorithm that we started class with in week 0 versus the more intelligent one of dividing and conquering, divide and conquer's worst case running time is instead what? Log n, right? Because we've said multiple times now that in the worst case, we're going to have to keep chopping the phone book in half and half and half and half until we get to one page where Mike Smith is finally listed. How many times can we do that chopping? Log n times. So this is something that we'll call logarithmic. All right, what about the best case running time of the phone book searching algorithm? Yeah, right? Because in the best case, and again, when you talk about an algorithm, you talk about a general input. You don't talk about an algorithm for finding Mike Smith. We talk about an algorithm for finding someone. Well, the best case running time of finding someone in a phone book, whether you use the linear algorithm or the logarithmic one, ultimately boils down to just constant time, right? Because you might be looking for Abigail Adams, who just so happens to be on the first page of the phone book. Bam, you're done. You don't even have to divide the phone book in half multiple times, and we'll call the running time of that algorithm constant. Whether it takes one step, now maybe it takes 2 steps because there she is on the page. Now I have to find what row she's in on the page. But those are just a constant number of steps, so we're going to generalize as just constant time. So what's the point of all of this? Well, we now, just as we did, have this means of comparing not apples and oranges per se, but apples and apples. If we have 2 different algorithms, linear search and then divide and conquer for the phone book, we can now say something qualitatively about which one is better in terms of its running time. And the notation folks tend to use for exactly that is this notation here. So just to toss out some jargon in case you see it anywhere, constant time we discussed, logarithmic time we discussed, linear time we've discussed. We'll see this running time often, n log n, Frankly, in 12, 15 years of computer science, I've never heard one human say supralinear, but that is in fact the formal term. N squared, we'll see in today and or Wednesday. That's called quadratic. More generally, if you have n raised to some power, that's a polynomial. And then there's n factorial, which is even worse than any of those, but you tend not to see that unless your algorithm is frankly downright stupid. So, couple of announcements. There's one handout today, very little code, but it's nonetheless out there. Lunch seems to have gone well, so we were kind of overwhelmed by responses. We ended up having a barbecue for 60 of your classmates, so we'll try to do another such thing some future Friday. More on that in a future class. If you've not yet returned sensor boards from the hacker edition of PSET 0, that's fine. Just hand them to one of the TFs in our little nook over here. PSET 2 went out the door on Friday. The walkthrough was filmed yesterday on Sunday. That video will go online by tomorrow. Office hours have been in progress. Do take advantage of those. And sections have already begun. So your assigned section, you should have been informed of by email. Either you went last night or your section's probably today or tomorrow. So do take advantage of those as well. And we also deployed, per problem set 2, this link on Friday. So there is now the bulletin board, which, if clicked, will log you into a little interface that looks like this. And the bulletin board is meant to serve a couple of purposes. One, it's meant to allow us to answer the same question once for many different people to benefit from the answer. It's meant to be an opportunity for you to potentially field each other's questions, so long as it doesn't cross that line of outright telling someone some answer. And what you'll find is that week to week, we'll add another category to the bulletin board for PSET 2, PSET 3, PSET 4, and so forth. And the goal of the bulletin board is to ask questions that you're pretty sure anyone can hear the answer to, anyone can see the specifics. But if you find that asking your question really requires that you show us your code, then continue to use help@cs50.net for that. But what you'll find more importantly, especially for those less comfortable, when you log in for the first time, even though it does authenticate you with your username and password, we have made your name the default value of student. So you can have that pseudonym, you can change it to something other than that, your own name or something fun, but realize the point of the bulletin board's anonymity is so that you can post what you fear is the proverbial dumb question, and no one else other than the staff as necessary is going to know that you even asked that question. So if that gives you more comfort, by all means ask more questions in that way. That was a lot to absorb. Let's take our 5-minute break. All right. We are back. So we do the following with Keynote. We have 8 doors here, behind which are little surprises. To reveal what's behind these doors, though, I need to solicit the ever awkward volunteer to come up on stage, if you will. Yeah, come on down. And again, you'll need to sign your rights away in perpetuity in a moment. So come on up. What is your name? Edward? OK. David, nice to meet you.
Nice to meet you.
Got a fan over there. All right, so Edward, much like a game show, we have these same doors. Whoops. Breeze will spoil the surprise. So we have 8 doors behind these pieces of paper here. So we have 2 arrays. So I'm going to start using the geek terminology. So we have 2 arrays, arrays of integers, each is of size 8. And you are now just a human who's been presented with a very awkward situation, the goal of which in this top array is to find me the number 3. And what we, the audience, hope to learn from this is exactly how you, the human, go about solving this problem. So if you would, on the top row only, find us the number 3, please. See the number 2? Oh, that was very good. We see the number 3. OK, so if you would, can you explain how you found the number 3?
Basically just went picking up the pieces of paper at random.
OK, so that was just chance then. It was not spoiled by the wind.
Right.
OK.
Just systematically go through and check all of the pieces of paper.
OK, good. So thank you first for spoiling my demo by finding it so quickly. But let's ask the question nonetheless. What is the running time of the algorithm that Edward just tried? Can we slap a label on this? Best case running time. Yeah, it's apparently 2, but 1 in the truly best case. So this is in omega of 1, we'll say. In the best case, he just happens to go straight for the right number just by chance or by some more sophisticated heuristic. And in the worst case, how long would it have taken you to find the number 3?
8.
OK, so 8, or more generally, big O of n. So we again have an algorithm that's big O of n, or omega of 1. So the question now at hand is, can we do better than that? So let's see. How could we fundamentally improve upon that algorithm? Any suggestions for Edward? Could we do better than big O of n? Because big O of n is great when it's only 8, but if n is now 4 billion, as we've discussed, n not so good anymore. Sorry? OK, so we could sort these things, right? There's an advantage that we've had all this time since week 0 of a phone book. Someone else, Verizon or whomever, has done the hard work of sorting that phone book alphabetically so that we can make certain assumptions. An assumption like, when I go down the middle and end up in the M's or the N's, I know the Smiths, the S's, are going to be to the right. Now, I didn't give Edward any such assumptions. And in fact, it's a little weird that 2 is over here, and yet 3 is over here. Kind of suggests that maybe these things are not so sorted. And in fact, there's 8, there's 1. So the top row is not, in fact, sorted. So if we now give you the added assumption that the bottom array of 8 and numbers is, in fact, sorted, how might you go about, without answering, just doing, finding us the number 50 in the bottom array? Different numbers, but they are now sorted. I see 171. Damn it. OK. OK, very good. OK, so what did you do this time?
Well, since you told me it was sorted, I assumed that that meant that it was either there was going to be some sort of pattern, so either the larger numbers were on the right or on the left, so I checked both sides.
OK, good. So as an aside, this demo was far more effective last year when we spent like 10 minutes on this. It was somewhat awkward, actually, because your predecessor spent a lot of time thinking about which number to reveal, thinking there was perhaps some trick to this, when really 5 minutes before class I'd written random numbers on the board. So you're doing much better. He was a good sport about it. OK, so bottom array is now sorted. Let's slap some numbers on this. Best case is apparently 2 again in reality. But formally, or asymptotically, anytime we start talking about big O and omega, we're talking asymptotically, which means as inputs get large, as n gets large, what generally happens to running time? So in the worst case, how long would your algorithm have taken? What? OK, n. And because why? What was your algorithm here? You said, I went high, I went low, but we didn't really get to see what you would have done next. In fact, let's continue this. Find me the number 52. I see 51. I see 61. Good. Back on top. OK, so pause there, because we know you're going to struggle now. So what was your algorithm? Now we have to push a little harder.
So I was assuming that they were sorted numerically, so that
OK.
the larger. So when you said 52, since I knew 50 was already down there, I just went to the same.
OK, good. So in short, I can summarize. So at first, you went high, because 50 is a pretty big number, certainly relative to the number 3 we looked for before. So you went high, didn't find it, then sort of thought maybe I was messing with you, so went left to look for the number 50 there. Didn't find it, but you did know it was sorted. So the rest of your algorithm after this guesswork at the beginning, try high, if not high, try low, was presumably to iterate then from left to right. OK, so we can still slap some formality on this approach, too. In the worst case, how many steps would that take, as you said? So, n steps, right? Because maybe you went high here. OK, that wasn't 50. Then you went low, not here still. And then you end up iterating over the n minus 1 remaining elements. OK, so big O of n. But again, best case running time is omega of, in your case here, is just 1. So in constant time. So this sort of begs the question then, how long did it take me, the person setting this up, to actually sort these values? So here, let's put you out of your awkwardness here. A round of applause if we could. Oh, legal form awaits. OK, so that begs the question then, how do we actually go about sorting these values? Because I kind of did it for free, right? I did it before class, kind of cheated by having the numbers pre-baked. But if you're just handed a bunch of numbers, as Edward effectively was, and I left it to him to sort those values so that he could then impress us with the running time of his better algorithm, how much time does it take to sort these numbers? Well, that, we'll see, is a much harder question to answer and a much more time-consuming problem to solve. But let's see if we can express now what Edward kind of did did, or in an ideal world would have done exactly, we can express this algorithm, or really any algorithm moving forward in the course, not just in C code, which gets fairly pedantic, writing out all the minutia. If we just want to convey the idea of an algorithm, just like we did in week 0 and 1, we can go with pseudocode. There is no formal standard for what pseudocode is. Different people take different approaches. The only important thing is to communicate your idea clearly without getting bogged down in stupid details like semicolons and parentheses, which add nothing to the logic and only distract from your idea. So I took the somewhat conventional but somewhat arbitrary approach of defining my pseudocode as follows. For linear search, as I called it, and this is what the world generally calls an algorithm where you start from here to here to here to here and move from left to right. So on input n, for n elements, for each element I, if I equals n, return true. So on input n for each element, yeah. So there are many different ways you can implement this pseudocode or write it, but it implies that there's an array of some sort, but syntactically it doesn't matter how we express this. So I'm going to take the approach of saying for each element I in my array, if I happens to equal n, the thing I'm looking for, go ahead and return true. But then per the indentation, if I never return true, the last line in my program says return false. And the answer is no, as was the case when Edward failed to find 52 because it just wasn't in that second array. But we can do what I was hoping he would do, but it's OK. I can do it myself. We can implement what we might call binary search, which is actually a direct application of the whole divide and conquer idea. Now, this algorithm looks at first glance certainly more complicated than linear search, but we've already seen how much time it saves on things like searching phone books and whatnot. So in theory, if I were searching for the number 50 here, and I didn't have this heuristic of going high or going low, because maybe that would work, but even Edward had to make a guess. Is 50 big or is it a small value? Well, in this case, it was actually a relatively small value because we had 50 here, but then 171 here. And in the end, though it was a clever trick, and he actually solved that problem very quickly to his credit, the algorithm itself ultimately boiled down to no better than just linear search. Because in the end, these clever heuristics, which in the real world clearly saved us some time and garnered him some applause, the rest of the algorithm, had he not been so lucky, is still the same linear algorithm. So what if I instead apply the Mike Smith approach? I go into the middle of my phone book, the middle of my array, and now I'm looking for the number 50. Well, we have some weird mathematical rounding errors that I'm sure we can work out with the round function or ceiling or floor or whatever. So I'm going to arbitrarily go here. Is this the number 50? No, it's the number 105. But just like in week 0, when I was able to tear away the problem of the phone book, I now know that my answer is definitely not going to be to the right. And so I can focus only on the remaining numbers here. Where do I go next? Well, I have essentially the same problem. I'm still looking for the number 50. I've still got an array. Upside is it's half as big as it once was. I can use that to my advantage performance-wise. So let me just go smack dab into the middle. I got to pick left or right arbitrarily because the math isn't working out beautifully. So let's pick this one. 51, not the case. But now I know it's this way. So now I know it's not here, 51 or 61. And I'm left with a problem that's a quarter of my original size. So already, fundamentally, I'm definitely moving faster than Edward would have given many more elements in his array, which clearly is going to be the case when we have more room and more interesting problems. So I've got 2 elements left. I arbitrarily go right, as I've been doing. Aha, the number 50. Now granted, and this is actually a useful takeaway, granted my algorithm was slower than Edward's. Edward took 2 steps. I took 3 steps. And yet I'm going to make the claim arrogantly nonetheless, my algorithm is better. Because as n increases asymptotically, the bigger and bigger n gets, the more and more you'll be impressed by the running time of my algorithm. And the more and more Edward's algorithm, in all fairness, just devolves back into a very slow but correct implementation of the same idea of search. Now, as an aside for the astute, this just so happens to be all of the computer science courses you're qualified to take after or before CS50. So keep that in mind at shopping periods time. But for now, the takeaway is that, very subliminal, I know. For now, or maybe it's not subliminal if I tell you what they are. So for now, we just need a way of expressing this. So there's many different ways we can express this. This is what I would call an iterative implementation of binary search. Thus far in the class, we've only talked about phone books and splitting them in half, throwing half away, repeating. But now that you have this ability to program a machine, you need to start expressing yourself more precisely. You can't just tell the computer, find me the number 50 or 52. You need to tell it how to do that. You need to teach the machine, so to speak. So one way we might implement that in pseudocode here is as follows. On the input of an array, where we call it array bracket 0 on up to n minus 1. So the length of most any array we ever discuss now is n, but the largest element index is obviously n minus 1, if we start counting from 0. And input k, where k is the value I'm looking for, I kind of need to implement this idea of binary search. So I'm going to define in italics here a variable called first and initialize it to 0. I'm going to define another variable called last and initialize it to n minus 1. And what the subsequent steps do, if you think it through as a future problem set may ask you to do, it's going to implement very precisely this approach. Here's n elements. I'm going to use my left hand as my left variable, my right hand as my right variable. And what is it telling me to do on the first step? Well, while first is less than or equal to last. So good. My left hand is indeed less than my right hand because it's to the left of it. What do? If let middle equals first plus last divided by 2. So what that math does for me is if I add this index plus this index, divide by 2, and take care of the rounding, that gives me a number in the middle. Let's say 105 for now. So middle equals that element there. So if k is less than the middle element in the array, then let last equal middle minus 1. All right, so I'm looking for the number 50. So 50 is indeed less than the middle element of the array. So what do? Well, the then condition says then let last equal middle minus 1. So here's last, here's middle minus 1. And already with just one iteration, we've seen how to translate a very simple idea, right? Split the problem in half and half, to something much closer to what GCC could understand, much closer to what you could actually code up in Nano. And if you follow the logic there, what you'll find is that iteratively, does my right hand keep moving closer to my left? Maybe sometimes my left goes closer to my right. If my hands ever cross, what's the implication, presumably? That it's not there. I'm looking for 52, and I went too far to the right, too far to the left. My hands cross because it's just not there. Or I end up smack dab on top of the number I'm looking for, whether it's 50 or 52. But what we've sacrificed here is this beauty of the original algorithm. What's really cool about divide and conquer is that it's so damn simple to explain. Take the phone book, split it in half, look at the element. If it's less than, go left. If it's greater than, go right. Repeat. Like there's this elegance about this where you just say divide the problem in half, check for something, and then repeat. This really clouds some of the simplicity of that algorithm. But we have this ability, it turns out, in C and in Java, C++, and all of these languages, particularly ones like Lisp and Scheme, which you could cover in CS51, of this feature of recursion. So it turns out that whenever we've said something like repeat, you can repeat by essentially applying the same algorithm again. Now, thus far in C, how do you implement an algorithm? Well, you write a function like Cypher or Caesar that implements some algorithm. So if we ever have to express this idea of repeat, maybe we can have a function just invoke itself again on a smaller piece of the puzzle. Well, what do we mean by that? Well, let's take a look at this very simple program. So this is sigma1.c. This is one of today's two printouts, two pieces of code that's printed out. So this is going to be a function that returns an int. It's called sigma in homage to the little symbol from your math book that looks like this and just implies summation. So I want to do this. So I want to sum up all of the numbers from I equals 0 to m. So if I want to express this much like the back of a high school math book would, this is I equals 0 on up to m of I. So I just want to compute the sum of all of the numbers from 0 up to m. OK, so not an interesting problem, but it's interesting how we can solve it. So here's one little sanity check. When we said last week you better get into the habit for your own sake and your program's sake of error checking, you've got to do sanity checks like this. Just because the function is going to be passed an int per the definition, per its signature, so to speak, per its declaration up here, that doesn't mean it's going to be an int you want. It might be negative. It might be 0, neither of which we want if we're trying to sum up positive values only. So I'm going to avoid the risk of an infinite loop by just doing a sanity check. If m is less than 1, return 0. So here's an interesting feature of C in a lot of languages. If you have to somehow signify an error condition, Some languages, as you may know from high school, like Java, have this thing called exceptions, where you can kind of raise a red flag and not bother returning a value at all. But languages like C require that a function return a value generally, in this case an int. And so sometimes you need to return what we called last week a special sentinel value, a special value that the person calling your function had better check for if they want to see if your function worked correctly. So it's not sufficient for a function like this to just print out, warning, m is less than 1. Because how is the code that called this function going to know that an error occurred, right? This was the point we were trying to make last week with side effects versus return values. A human can see side effects. A computer can only see return values. So if we're trying to write code that calls this function, and I want my code to be able to check if an error happened, I can't rely on printf. I have to rely on return values. So what value could I return in the event that the input just doesn't make sense? Well, here I arbitrarily chose 0. What might have been another reasonable value to return to signify essentially error? -1, right? Why? Well, just because. If you return a negative value, clearly the caller, the function that called this function, can infer by getting back a negative number when the whole point of the exercise was summation of positive numbers that something went wrong. So think too back to last week when we mentioned very briefly, because we'll come back to it, that getString sometimes can return a bogus value or not return a string per se. It can sometimes return a special sentinel called what? This was null. So we'll see this many more times. It hasn't really come up yet, but null in all caps is a constant that signifies there is no string, but I'm a function with a return value. I have to return something. So when you start consulting man pages later in the course for new functions that you might want to employ, you'll need to check the section of the manual that says what return values does this function have, because sometimes you'll want to check with your own little if condition, did I get back a value I care about? Well, this code is easy. So now once I've done this sanity check and I want to sum up the numbers from 1 through m, or equivalently 0 through m, I'm going to do this. I'm going to declare a variable called sum. It's going to be of type int, and I'm going to initialize it to 0. I'm then going to iterate from I equals 1 on up to m equals, less than or equals to m, and then I++. And so what does this code ultimately do? It just sums up all the numbers from 1 to m, or 0 to m. All right, so if I see this in action, let me go ahead to a terminal window here. I've got, let's go ahead and open a new one. Let me go ahead and SSH to nice.fas.harvard.edu. And if I go into my CS50 directory, OK, and lecture 3, week 3, OK, sigma 1. So this is the same exact code. Notice that, oh, why do I have this at the top of this file? What's the point of declaring sigma as a prototype up there? Yeah, so you remember from last week, if you are calling a function that just so happens to be implemented later in the file, but you're trying to call it from main, which apparently I am. So this was not on the slide a moment ago, but apparently I am, in fact, calling sigma from main. It's a stupid detail, but you've got to proactively tell the compiler, hey, there is a function in this file called sigma. It returns an int. It takes an int. Just know to expect it eventually. And realize this, too. It turns out that when you declare a prototype for a function, you don't have to provide the names of the variables. All the compiler needs to know at that point in time is what types of variables it has as arguments. So you can literally just write int, or if it takes 2 arguments, int, comma, whatever. So either approach is fine. I could have specified the name of the variable up here with int m, but it just isn't necessary. So I tend to be fairly minimalist when I write the code. All right, so here's the function down there. And notice one other detail, just to make this more compelling. Why did I not do this? Because this was a question asked, I think, on the bulletin board this weekend. Why did I not do, say, this? There's probably a couple problems here. What's one? Yeah. Yeah, so there's a logical error. I'm declaring int, I'm reinitializing sum to 0 every time, so that's not good. What if I did this, as I've seen before? I can sometimes initialize 2 variables to a value in my for loop. So that seems to be OK, but what kind of error am I going to run into next? Some of you may have. Yeah? Oh, this is, don't stretch like this during class. OK. Yeah, in the back. Exactly. Remember last week's discussion of scope. So generally, when you declare a variable, say inside curly braces, or in this case inside the for loop, that variable only lives inside of that for loop, which means this math is perfect. We initialize sum to 0, we keep adding to some I, but the moment down here I try to return sum, my compiler is going to complain to me sum not declared, even though it is, because it's outside of the scope. So it was very deliberate a moment ago when I declared this variable outside of the loop, and it's so that it would remain in scope the entire time. All right, so let's go ahead and save this. Let's make sigma 1. I'm not going to bother typing GCC and all that because this handles a lot of the magic for me now. I'm going to go ahead and /sigma1 to be ever so clear for security reasons that it's in this current directory. Enter. Positive integer, please. Let's say 10. OK, hopefully that's correct. 9. All right, let's do one I can check quickly. 3. Yes, I'm pretty sure. 3 plus 2 plus 1 equals, in fact, 6. So it feels like this code is correct. But turns out we can implement this in a very different way. So how did this function get called first? Well, here is an example of where do while is useful. We said last week that do while is often useful when you want to ask the user for something, give them a chance to give it to you, and then reprimand them or ask them again if they fail to provide what you're looking for. So here's exactly that scenario. Declare an int called n. I'm going to do the following. Tell the user, positive integer, please. I'm going to then use getInt from the CS50 library to get the n. And then right here, rather elegantly, am I going to check within my while construct if n is at this point in time less than 1? Do it again and do it again. So this is a general approach, do while, to getting user input. And the result, to be clear, is that if I try messing with the computer and say -123 or -6, it's just going to keep pestering me. But remember my random word of last week, monkey, why does it say retry instead of positive integer here? Yeah, so this is thanks to getInt. So as the name getInt implies, getInt will do its best to get an int from the user, but it doesn't guarantee it's going to be positive or negative or anything like that. It just gets you an int. So it turns out we can implement this same function in a really interesting way that hints at the beauty of this thing called recursion. A function is recursive if it calls itself. Now, on first glance, or first here, that might be a little worrisome. If I'm a function and I got called with an input, and I try to solve that problem by calling myself, that should immediately shout infinite loop. Bad stuff happens. But hopefully, there's some way of making sure that you don't keep calling yourself in perpetuity. And there is. It's called a base case. So notice, this implementation of Sigma is only 4 lines of code. And frankly, if I got rid of some of the indentation, all of that, it's really like a 2-line program, maybe even a 1-line program that implements exactly the same function, exactly the same formula of adding numbers together. So what do? On input m, I ask myself, is m less than or equal to 0? If so, just return 0, because bad things will happen if I start trying to deal with negative numbers. Now, apparently, all I need to do to answer this question is call myself. And this is where you get this weird sort of circular magic. Notice that all I do otherwise, after my base case, after my sanity check, is return the result of m, the value I was passed, plus sigma of m minus 1. Now that alone actually works. If I go back to my terminal and I compile sigma 2, and I run sigma 2, and I give it the number 3, I get back 6. If I give it 10, I get 55. In fact, it works. And yet, how is it doing that? Well, let's see. So it turns out that this problem of adding all the numbers from a 0 on up to m, or equivalently m all the way down to 0, is pretty easy, even conceptually. If you hand me the number m and ask me what's the sum from m down to 0, well, I could say, all right, well, it's m plus the sum of all the numbers from m minus 1 on down there. All right, so let me ask you again. What is the sum of m minus 1 on down to 0? Well, it's m minus 1 plus the sum of m minus 2 all the way down to 0, right? You can be this really argumentative human pushing back on the person in wise-ass form. Oh, well, it's just the answer of m plus the rest of it. Well, what's the rest of it? Well, it's a little bit less than the rest of it plus the rest of that, right? You just keep taking this bite, minus 1 out of each piece of the puzzle, and that would seem to go on forever, but not quite, because eventually when I get over here, my last piece of the puzzle is going to be m equals what? 0, and that's when I hit this so-called base case, when all of my answers now start to bubble up. In a sense, I was kind of passing the buck, by playing this game with the person asking the question. Well, what's m plus all the numbers below it? Well, it's m plus the sum of all the numbers below it. What's the sum of that? Right? Eventually, we bottom out at 0, and then I finally start getting useful answers back until the end result is precisely the same. But what's then the point of all of this? Well, and again, this is something that you perhaps begin to see eventually, and maybe you never see. But there's kind of a beauty about expressing something as silly as addition of numbers with just this recursive scenario. And this will be a very representative approach to solving much bigger, much more interesting problems. But there is a catch. Let me go ahead and run sigma of 1, my first version, on 100. That works pretty well. How about 1,000? Works pretty well. How about 10,000? Still working. 100,000. All right, then eventually I'm going to start to exhaust an int. OK, so now I exhausted the int, but we would expect that. Let me try now to run sigma 2. So it's a more elegant solution. Feels like it should be even faster because there's just, frankly, fewer lines of code. Well, let's see what happens. Sigma 2 of, 10. That works. How about 100? That works. How about 1,000? Still working. 10,000. All right. 100,000. OK. Come on, break. Ooh. Now, some of you have seen this problem, too. And we actually smiled. So in all fairness to the anonymized student asking the question on the bulletin board, is it OK if my program quits by saying segmentation fault, core dumped? No. So this is a bad thing. So bless your heart for asking. But this is not a solution to the problem. This is, as I said in the bulletin board post, frankly, or maybe this was a private email. But, so as I said in this response, this is sort of the Linux equivalent of Microsoft Word just hanging, or your Mac program just freezing, or unexpectedly quitting, which is ever so annoying. This is sort of the equivalent in the Linux world. But fortunately, now that we're the programmer and we're not just the user, the fact that it's dumping core, so to speak, is actually useful. So for today's purposes, segmentation fault means something bad happened with respect to memory, because memory in your computer is generally modeled as a bunch of segments. So segmentation fault means something went awry with regard to memory. Core dumped means that something useful was left in my current directory. If I type ls for list, notice that I have this file called core. Core is actually a file containing pretty much the contents of the computer's RAM at the moment in time when my program screwed up. Now, it's not all of the memory from all users on the system, because that would be a security concern or privacy concern, but it's diagnostically useful, we'll see, in a week or so once we start dissecting the insides of that file. But for now, the question is quite simply, why did this happen? Why does it not appear capable of handling the same number of zeros as the first version? Now, granted, the first version still broken, but it doesn't ultimately choke in the same horrific way. So what is happening in sigma 2 that's not apparently happening in sigma 1? And again, some of you have tripped over this, and frankly, by the end of the semester, you will all have core dumped. Why? What might be going wrong here? So it has to do with memory. Where is memory getting used in this program? I don't even see any local variables other than the parameter called m for this function. So where is the memory getting used? Like, why do I have memory problems? Yeah, so when I call sigma, it does what? So it allocates a bit more memory. And in fact, let me remind of this little picture from last week, and we said we'd come back to this. This, recall, is the rectangle that represents your computer's RAM. But recall the more important point from last week, that anytime you call a function, a little chunk of memory does get allocated on the so-called stack for that function. And that chunk of memory we called a frame. So if sigma is called by main, and then sigma calls who in version 2? Sigma, and then sigma calls sigma, and then sigma calls sigma. You know, even though on this picture I've not implied that there is an upper bound on the amount of memory you can allocate, but in reality there is. On a typical system, a given program often cannot use any more than, say, 2 gigabytes of memory. Now, that's a lot of memory, but not necessarily for programs like Photoshop, and so there actually are some interesting real-world implications here. But the point is that that rectangle eventually has a top to it. And if you keep trying to put more and more stack frames on your memory stack, eventually you're going to overlap with something else that needs it more. In fact, what did we say is at the very top of this rectangle, if briefly, last week? Sorry? So there's there's global variables, but there's also the text segment, as we called it, the program itself, your zeros and ones of your program itself. Now, this doesn't mean that you're overwriting your program on disk. It doesn't mean you're erasing your code, but it does mean that the operating system is just going to bail altogether if you try using memory that already belongs to something else. So let's go ahead and end there. And on Wednesday, we'll figure out how to work around this.